Now let's talk about something more practical, syntax analysis, and I will show you a number of tools and some software which does the job. So let's start with the definition. In 1959, they were developing programming language which was later known as Algol 58. John Backus introduced a meta-language to describe formal grammar. 1959. Remember, in 1956, the idea of formal grammar showed up. In 1959, 3 years later, they started to use it in the designing of a programming language, and they introduced the notation. Because all we saw before, there were just arrows, lines, and more like mathematical formulas, but not something you can type in. So they suggest to move that into the code, into the text, and define the same formal grammar as we did in the formulas, but in the text. And then later, 4 years later, Peter Naur joined that activity, or maybe he was there before, I don't know the details, but in the end, Donald Knuth suggested to call this notation Backus-Naur 4. So the way, probably you've heard about it, BNF. If you don't, I'll show it up to you right now. So BNF, or extended BNF, which was proposed, let me calculate, 14 years later, after all that, the BNF showed up in 1963, and in 1977, 14 years later, by Niklaus Wirth, he suggested a notation which was more powerful than BNF, and it was called eBNF, extended BNF. And this eBNF notation was even standardized by ISO organization, but unfortunately, we still use this BNF quite informally and quite subjectively. So you can even use your own notation. Let me show what this BNF means and what is eBNF. So if you write for our, again, programming language, if we say that we were doing this before, let me copy it. This is our formal grammar. It's not computer digestible, so you cannot send this to the computer and make the computer understand it. So in order to make something more, as far as I understand, understood by the computer, even though this BNF notation is not really used, to my knowledge, is not really used for computers. It's mostly used for documentation, for books, for papers, to describe the notation. So in the BNF, it would look like this. It will look like this. Program, sometimes it's like this, equals to program equals, they don't have epsilon, they don't have empty here, so they say, but they are more powerful, so you can define it here like line in the double quotes, and then you say program, and then like this, and then you say line equals to command, like we did the space, and then arguments, and so on and so forth. So it's the same, but in a textual format. But usually people use this format, and this is more powerful. Why? Because sometimes you can do things more conveniently. For example, let's say you want to let's say we want to describe the list of arguments. In eBNF, we can do it like this. We can say, like in our case, number. Remember how difficult it was for us to do it with recursion and everything. In BNF, you can say number, and that's it. This. So in one line, you do the same, which we did in 2 lines, but this is much more readable. So the square brackets means optional, And the curled brackets means repeated a number of times, or maybe 0. So we say our list of arguments may be nothing because of these square brackets. It means that skip, like in regular expressions. No, in regular expressions, it's different. But so you say you can skip what's inside. So basically args, it could be epsilon, but they don't use epsilon, they use square brackets. So you say maybe nothing, but if it's something, then it could be a number, and then the comma in the double quotes. So the comma and the number, and you can repeat it multiple times. So it's just more convenient way to describe formal grammar using this notation. So in this notation, they have square brackets, they have curled brackets, and they have, and basically that's it. That's the most important. Yeah, and they have the options. So for example, you can say command. It's either print or like this. So one, another with the bar here, and with the round parentheses around them. That's the same as in regular expressions. So that's basically the entire syntax of EBNF notation. Curled brackets, square brackets, round brackets, and this sign on the left. That's probably it. So nothing fancy. And people change this format the way they want, because there are no software. I mean, they could probably, this software exists, but there are no really widely used piece of software which would say you need to write it this way, otherwise I'm not going to understand it. These software just don't exist. So when you write, for example, in your diploma work, you say, I invented a new programming language. Here's the EBNF notation for my language. And you write it the way you write it. If you make your own syntax there, and you say, instead of, maybe instead of square brackets, I'm going to use this notation. I'm going to use these brackets. And that means optional. So nobody going to punish you for that, because it's just a convention. You just say it in your paper that by these brackets, it means what's inside is optional. That's it. So it's pretty flexible. And this is what people who were trying to standardize that, they complain about. They say this EBNF, if you open a number of scientific papers which talk about some new programming language of you, or maybe new library, something new, and you compare their BNF notations, how they use it for describing their syntax, it's going to be all different. In one notation, they use it this way, another notation that way. So it's just a zoo. People don't really have a common ground of what's the right way to do. So that's the way it is. That's how it works. So now let's talk about lexical analysis, tokenization. Tokenization, lexical analysis. So when we analyze, when we build a compiler or build any computer, any software which is supposed to understand what we do, then the pipeline looks like this. This is the input text, which is a stream of characters. This input text comes into a so-called Lexer. The Lexer produces the stream of tokens, and then this stream of tokens is sent into the, how to say it right? I would even say that stream of, yeah, and then there goes the parser. I think I understand it right. Which generates the parse tree. Each token, in case of this Lexer, each token is, let's say this is the input text. We say print 10. That's our input text. The Lexer will break it down into, the stream of tokens will look like this. So this is what's inside is called a lexem, and this is, well, this is together. I would say it's a, yeah, it's, let's say it's a token, but token actually is all together. So this is, so token encapsulates the reason for the existence of this token. So print is basically the text which Lexer captured and encapsulated into the token, and this is the token for you. And this is probably the type of the token. I don't know what's the right name for this. What is the command, space, number? So I would say it's, let's call it, maybe I'm wrong, but let's call it the type of a token, something like that. So we take this print2, the Lexer generates these tokens, and then the stream of token goes into the parser, and the parser generates the parse tree and says, you know, it was a program. In the program we had a command, then we had a space, and then we had a number. That's what it is. So the parser needs to know about our formal grammar. Well, they both need to know about the formal grammar. The Lexer as well needs to know about formal grammar. But usually it's broken down into two parts, the Lexer and the parser. That's how it's, and I'll show you how it is designed, how people usually do it. But sometimes, like I showed you before, sometimes people do so-called parseless, so-called, what's the right name for it? Yeah, not the parseless, scannerless parsing. So this guy, Lexer, is also called a scanner. Is it double N or one N? Scanner, double N, sorry. This is scanner, and that's why it's scannerless. So sometimes this part is omitted for the Lexer, and they just go directly to the parser. So the parser does both jobs, but usually they split it into two parts. First, they go through the text character by character and breaking it down into tokens. And then when the tokens are there, then we can deal with the tokens and go through the grammar and decide how the tokens fit together, how they stay together. And usually these Lexers are implemented like the state machine, like the DFAs, definitive finite state automatas. And let me show you by example how it may work. Let's make a simple language, even simpler than we had before. And the program will look like this. And by the way, I wanted to ask you, do you understand why I put the numbers on the left side? What does it mean? Let's say this is my program. 10 print, 20 render, 30 exit. Why the numbers? What do the numbers mean? Why do it this way? No, basically, who knows the language BASIC? It was a language long time ago. You don't know this language. So, so that was the language which students were studying 20 years ago. It was the main programming language at that time. And in this programming, it was imperative language where each line was an instruction. So you go line by line. This program looks very much like the BASIC program. So every line goes one after another. And because the computers at that time, they didn't have, most of the computers, they didn't have the interactive editors like you have right now, where you can move the cursor up and edit the text on the top. So you can only enter the line, click enter, and the screen moves up. You again enter the line, click enter, and the screen moves up. That's how they teach me programming. So you cannot just move the mouse on the top. There was no mice at that time. So there's no mouse, only the keyboard. And at the keyboard, there are no character up. So the cursor always stays at the bottom line of the screen, always. What you see on the top of the screen is something that scrolls up, scrolls up, scrolls up. So when you enter the program, you start this interpreter of the basic programming language. You type 10 space print, enter. And it goes up. And the computer remembers, okay, now we have the line in the program print. And the position of this line is 10. And then you type 20, print something else, enter. By giving the number on the line, you're telling this interpreter that put this line after the line 10, because 10 goes before 20. And then you decide, okay, I forgot, I need a line between these two lines. What do? You say 15, something else, enter. And the interpreter injects your line between 10 and 20. And then if you don't remember what your program looks like, you say list, you say enter, and it prints you the full program, shows you this is your program. You just read it and say, I forgot. You enter another line, inject it there, and again, list. It shows you the full program. So that's how you program. That's how it was. So that's why the numbers, yeah, that was crazy. And that's why the numbers. So I'm just showing you the language. And imagine, and this 10, 20, 30. And in that language, if you want to jump, there was no, it was, the language was not structured as now we have the blocks of code, which you separate with the curly bracket, and then you put the code, and then you say, if something, then execute this code, or while something, execute that code. In that language, there was no possible to do stuff like that in most cases. So there was jump instructions, or go to instructions. And for example, it was possible to do this go to 20. And that means jump to the line 20, because all lines are numbered. So that's why when you do go to, you show exactly the line where to go. And then you can say maybe something like this. If A more than 5, then go to 30, something like that. And that was the syntax of the language. So you compare and you jump. But it was not possible to do if, then, and how it became possible after then, and then some code, and then close the block. It was not possible. So each line is an individual code executed completely separate. So that's why I suggest this syntax for the parsing. Okay, so let's imagine this is our program, and we want to parse it into, we want to convert it into the stream of tokens. So we want first to understand what are these things. What is this? What is this? What is this? Basically, they are the terminals. Okay, sorry, that's right. So these are the tokens, are the terminals. Exactly. So when we take, I was thinking why we need the Lexer. So we need the Lexer in order to turn the stream into the terminals. And then when we have all the terminals together, like going one after another, then we apply the formal grammar, which has non-terminals, the variables. And in the formal grammar, we have the notion of the program, of the line, of everything. But what's incoming to us is the terminals, terminals, terminals. So all of these elements of the input stream, we need to break it down into terminals. And once we have a stream of terminals, then we can apply formal grammar and receive the parse tree. So we will create the non-terminals using the stream. So we will decide, this is a line, and this is a command, this is the program. That's what's happening. So the Lexer makes terminals. The parser makes non-terminals. So the question is how to turn that into the stream of non-terminals. I would do it this way. I actually have two ways, but let's start with the simple one. We have the starting state when we start, when the program is, we just start to parse this text. Actually, it will look not like we see it here, but it will look differently. It will look like this: 10. Print, end of line, 20, let's say exit, the space here, the space here. This is our input stream, right? That's what's coming in. And we're starting with the starting state. From this point, if from 1 to 9, we see the character, we see the character from 1 to 9, it's 1, 2, 3, 4, whatever, up till 9, we move our machine, our automata, to the state 1. In this state, we stay until when we see characters, more characters coming in from 0 to 9. So the character 1 came in, we stay at this, we change the state, we say, okay, now we're listening to you, now the token with the number is coming in. And we listen. More numbers are coming, we still stay at this, we still stay at this state. Then, when the space happens, after the number, we change the state. We move to the state, let's call it 2. And now we're here at state 2. From here, if from A to Z, if any English letter is happening, we move to the state 3. In this state, we stay and listen to A to Z characters. So we're here, moving to here. And then /n happens, so end of line. If end of line happens, we move here. And that's basically it. This is the entire automata. We moved here, so we're end of line, so we are again here, again at this state, again listening to numbers, again space, number, and that's it. That's the machine. When we exit this state and this state, we emit, I would use this word, emit the terminals. Here we will say it's a number, and here we would say it's a command. And encapsulate what we accumulated. When we moved into this state, we just empty the accumulator, it's empty. Well, it's with this ladder which we arrive with, and then we stay there, accumulate, and then 10 is there, we exit it, and we put it into the stream of these tokens. Here we accumulate, when it's done, it says, for example, print, and we store it. We have the terminal. That's basically how any Lexer would work. However, I can suggest you a better solution. And I can show you what is, first of all, let's see what is the problem with this machine. First of all, the problem here is that if you take, for example, this text, oops, then we probably expect this to be a stream of numbers. Number. But this machine will not parse it. Because you can see why, right? Because I start from here, it's okay, we move to the state 1, we read this token, we emit the token 10, but then the space moves here to this position. From the state we move here, but at this position we expect to from this position we can move further only if here we're going to see A or Z. I mean the letter. But we don't see it there. So we get stuck here. Not stuck, but here we're going to get an error. It will say, I don't understand you, because from here only the letter is expected. So this machine can only parse the text which is in this strict format. So it expects the tokens to go into specific order. The number. So this machine knows too much about the grammar. It knows that after the number goes the command. Maybe it's good, maybe it's not good. Depends on our intention, what we want to achieve. We can create an alternative machine which would take this string and generate the tokens number. So it's going to be 4 numbers in this case. Yes, the parser is not going to, the parser which will apply later is not going to like it, because the 4 numbers is not what our language is. So the parser will object about it. The parser will say, these numbers after numbers is not according to the formal grammar. But the Lexer will at least understand the tokens, understand these terminals. So this machine, this automata, cannot do that. So I would create a different one, this case, which would be more generic, more suitable for any purposes. I would do it this way. So let's say again we start at the position S. Again, to remember, that's the input. /n 20, again maybe exit space. So we start from S, and from S we can go to, if we take 1 on 9, we go to position 1. From position 1, like before, we read the numbers and accumulate the number. Also from the position S, we can go to another state, state 2, which will, if we get the space here. If the space is provided at the starting point, then we go to the position 2, which can read as many spaces as possible, and stay in the position 2 while you are in the space area. While you're reading the spaces, you stay at the state 2. And also from the starting point, we can move to the position 3, which will read the letters. And it will stay here reading the letters to itself. Again, so as soon as the letter arrives, you just move to the same state. From here, if, for example, you're reading the letters and then a number happens, then you move here. And then a space happens, you move here. And from the space, if the number happens, you move here. Okay, maybe like this. Or maybe, yeah, sorry, this is 1 here. Because we only want the proper integers without the leading 0. So basically we make from anyone to anyone. From here, if the end of line happens, then we move here. From here, if end of line happens, we move here. From here, if end of lines happens, we move here. So each to each. So from this, in this position, we accumulate spaces. In this position, we accumulate letters. In this position, we accumulate numbers. Here, we accumulate end of lines. And this machine can read whatever it is. For example, it can read this text, space, space, 10, space, /n, space, exit. It starts from here. It sees at this position, it's a space, so it jumps here. Then it moves here. The space is still here, it stays. Then it says number 1. From number 1, it moves here to the position 1. Then it accumulates the number. It moves there. Then it sees the space. From here, we move this line. We move to space here. It jumps to the position 2. Then from the position 2, it sees end of line. End of line goes here. And so on and so forth. So from any state, we can go to any state, depending on what it's coming to us. So this machine can perfectly parse any text as long as the text contains numbers and letters. Numbers and letters and spaces and end of lines. And then after that, the parser will decide, is it okay, is it the proper text, or maybe the mistakes are there. Yes. Now let me ask you a question. How do you think? Look at this code. It's first tell me what is the language. What is the language? C. So how many tokens are there? How many terminals or tokens? There are no spaces here, so imagine there are no spaces. So it's all together. So what's the number? 4? 5? 10? 7? Let's count. Okay, what's the first one? Printf. What's the second one? The bracket. What's the third one? String. I think this is the second, the third token. The string altogether, yeah. What's the fourth one? Comma. Then? Ampersand, that's right. Next one? I. Next one? And finally? So it is 8, right? 8 tokens. I found this question in one book. Because people, I understand why the question is. So people may think that these are also tokens. I think that's the trick. So they're trying to get the understanding from students that they understand that the string goes together as one token. So what's inside the string is not being parsed is not being recognized by the Lexer. So the Lexer just starts with a quote, with the double quote, and then goes until it finds the final double quote. And then everything which is found, it just takes and says, this is the token. This is the terminal. All right? So that's tokenization. Just turning the string, turning the text into token. And then goes the syntactic analysis. And also they call it not only tokenization, but lemmatization, because sometimes it's lexems or lemmas, different words for that. So you can call it token, you can call it terminal, symbol, you can call it lexem, lemma. I don't know the difference between these things, but you interchangeably, more or less, can call them. Maybe I'm wrong. In most cases, when you will write something which will read the input string and will parse that input string, you're not going to do these machines manually. You're not going to build this parsing or tokenization manually, because it's time consuming and you will probably make mistakes. Like I showed you before, this code, it was, like I said, it was okay because it was small. So you will use parser generators, or maybe you've heard the term compilers. So software which make you a compiler. And this software may consist or usually consists of two parts, the Lexer and the Parser. Historically, there was the two software tools for Linux, for Unix, not for Linux, for Unix, which were used actively. The first tool, who knows about that? Flex and Bison or Lex and Yacc, so probably you use them, right? Or you've just heard about them. Did you use them? Use them. So, a little bit, yeah? Okay, I will just briefly explain you how they work. So they stay together, again, in order to do tokenization or turning the text into tokens and then parsing the text. Let's start from the setup. The first file is the file for the Lexer. Let's create a very simple, very primitive Lexer, which will read the text. Yeah, let me. Don't want to break it too much, so hold on. So let's write a very simple Lexer, which will take an input stream from us and turn it into a stream of tokens, which we will see. We will see what tokens it generates. The moment we will have the input stream will have numbers and letters, and we want all numbers to be grouped together as integers, and then we want all letters to be grouped together, and we call them words. So when the collection of, you see the collection of digits, a number of digits will come up. So at this state, we will accumulate the digits. We will print that we just received the integer. When we find the letter, we will see we found a word, when a number of words came to us. When the space is there, we're going to ignore. When the end of line is there, we're going to ignore. Okay, maybe end of line, yeah, the end of line we ignore and the space we ignore. So that's a very primitive program, meta program for the flex. So the flex will take this program and generate a real C program, which will do all this manipulation with the state machine. So it will check the states, it will move us from state to state, it will do a lot of things. So let's see how it will happen. Let's compile it. You say flex foo x. It is compiled. Let's see the file that it generates for us. So this is the file which a lexical scanner. You see the scanner or Lexer or lexical scanner. Basically, lexical scanner is short for the Lexer is short for lexical scanner generated by Flex. You see the size of this file. You're not going to write this manually. So it's almost 2,000 lines of code just to read a letter and number, letter and number. You can do it in like how many lines of code? 50 probably, if you don't do this formal grammar or whatever. It's very primitive. But they introduce you a whole framework. They do a lot of things here which actually work. So if we compile that, what's the name of this file? Yeah, what is the... They generated this file. Main. Okay, they want me to have main. So they want me this. They want me to have main, and I have to do this. So call actually the Lexer. Let's compile again. No, let's generate again and compile. Okay, now we have the file. Let's run it, and let's do the input. Okay. It's unreadable. Why? Let's compile again. Flex. So Flex generates C code. Then GCC compiles C code. Then we have a binary which we run, and it waits for the input. We provide the input. Hello, 42, y, 45. And it says word, integer, integer. See that, right? So we provided a string with spaces. It print word, integer, and it waits for something else. What if we do something else? It also understands us, because the end of line it understands. It ignores the ends of line, it ignores the spaces, and when we enter the number, it understands that in the input, the token is there, the token arrives, it continues to read the input, continues to read and parse what's coming in. If I do something else, then it's an error. So it's a default reaction to the error. If it doesn't understand what's there, no action this is called action code. What stays after the pattern, so this is the pattern, this is action code. So after the action, if the action code is empty, then nothing happens. If the action code is provided, then the action code is executed. But the default action code in this Lexer is printing what's coming in, and no token is generated. So that's as easy as it could be. Okay, that's just a Lexer. So we cannot yet do the parsing. It only generates, like we discussed, it only generates terminals. And now the next step after the terminals is to build the parser. The parser is built by another tool called Bison. Bison, or before it was Yacc, yet another CC, compiler. So for the Bison, we create the code similar, and they connect to each other. How they connect to each other? In Bison, this is the file for Bison, this is the header, ignore it, we just need it. First, we define the tokens, let's call them the types of tokens, or the tokens with which we deal in our program. So these are the terminals. These are the terminals, and this is the part with the formal grammar, with the grammar, with non-terminals. So for example, input, we can call it not the input, the program. Let's say I created a small program which can understand the date. When you type something in, it's either a date or a sentence. So you either provide a date or a sentence. And then the second rule says the date is integer plus integer plus integer. So this is the terminal, this is non-terminal. So we say the date is basically 3 terminals going one after another. If this is found, then print the date. Date is found. Or the sentence here, I don't know why, but sentence like this. Okay, I'm saying the sentence could be empty, or the sentence is a collection, basically sentence is a collection of words, or maybe an empty sentence, but I don't like it. So let's say the sentence is okay. So sentence could be empty, or sentence could be with a number of words. If we find this, we print sentence. Again, we define main here, and we remove main from here. So now Bison will generate the C code for us. And when Bison generates the code for us, then let's see how it can do it for us. Bison minus D, I believe, foo y. Yeah, the Bison generates 2 files. One file is called foo.tab.h, and another file is called foo.tab.c. Whatever it is. So let's see at the H file first. We can open it here. So if we open the flex file on the left, and then the Bison file on the right. So this is our code for the Lexer. This is our code for the parser. You see, that's how they interact to each other. So the token word, the token int, they are defined on the right side, on the Bison part, on the parser part. And here we do this trick. Return int. I'll explain it now. Return word. So Bison is a client. When we compile all this together, we have basically 2 modules. Bison is a client for the Lexer. Bison is calling the Lexer and saying, what is the next token? And the Lexer returns one of these 2 numbers. It says the next token is word, or the next token is int. If nothing is returned, then the Lexer, then the Bison continues asking, okay, what's the next token? Give me the next token. Here, for example, if the spaces are coming, then the Lexer doesn't return anything. So you see there's no return here. So the Lexer will continue scanning the text, moving forward until this action code is reached, and then the int or word are returned. These numbers, basically they're numbers. So int, word, they're just, I don't know, 7 or 8. So we can replace 7 or 8, and here we can say sentence. You know, they're just numbers, just constants in the C, in the C language. So Bison is a client. And here in the main function, we call YY_parse, and YY_parse will call YY_lex from the Lexer. So they communicate like this. The parser is a client. It's not like the Lexer is creating, already created a stream of tokens or like a list of tokens and delivered to the parser. It's not like this. They work in a streaming mode. So the Bison is asking, what's next, what's next, what's next? And the Lexer is providing the result. So that's why when we compile them, the Bison, you see these words are defined only once. So we don't want to define them here and here. So that's why when we compile this file, then Bison generates the H file, the header file, which should be quite small. You see, like I promised you. So the word is the number and the int is the number, but these numbers are generated by Bison. It's a small file. You see, just 50 lines of code. So all it does, it just defines the. Oh, you see the token type. So I was right. So that's the token type. The token type could be either word or int. They define the headers, and this file must be included now in the Lex file. So the file is generated by Bison, and when we will compile the Lexer, we need to include this file, because otherwise it will not know what is int, it will not know what is word. So we have three files. The one for the Lexer, the one with the sources for the Lexer, one with the sources for Bison, and the header file, which helps them communicate to each other. So let's try to compile. We already compiled it. Let's do it again. We compile Bison. After that, we compile Flex. And then finally, we do the GCC together. We have two C files right now. You see, one file is this. One file is foo tab C. Another one is Lex. So funny names. But what can you do? So we do O out. We compile foo tab C and we compile Lex. Done. Surprisingly, no errors. And we do A. We execute it. So let's see. Let's enter the date. 12. Wrong date, but still. Date. It understands that's a date. Let's say hello world. Syntax error. Let's try again. Hello world. Sentence. So this, it understands the hello as a sentence and the world as a sentence. Let's try again. It's funny. Hi, you, my friend. So 4 sentences. Wrong. So it understands it like a sentence going after another sentence. Let's see what's wrong with the rules. These are the rules. So we say sentence is a sentence and then a word. I think that probably, no, I think that this action is positioned in the wrong way, because this rule is applied 4 times. It's recursively. So we say sentence is a sentence is a sentence. So it applies this rule 4 times, and that's why it prints this 4 times. So I think we need to say that, I don't know what's the right way here to print it correctly, because definitely it is in the wrong place. Yeah, print here is not positioned right. But let's see. Yeah, and why it says the error in the end? Because it only expects one date or one sentence, but not more. If the Lexer before, remember, we were entering different texts and it was always telling us what are the tokens. It was working endlessly. But this guy is not doing it like this. It only expects, it has a strict grammar, and it says the program is exactly one date and it's exactly one sentence. We can change that. Let's remove this nonsense, because we definitely print something wrong. So we can say that let's make it more. So let's say the program is a number of dates and sentences. So I think that here it is possible to say that the program is, let's say program, like we did before. A program is a line and the program. And then we say a line is a date or a sentence. Let's do it like this again. So we compile the Bison, 5 useless non-terminals and 7 useless rules. 7 useless non-terminals. Why we have useless non-terminals? We say program is a line. And you see, by default, it understands that the first rule is the starting one. Because you see, we nowhere say that what is the starting one. So I just assume that it takes the first one, and this is the starting one. So now our question is, what's wrong with our text? Program is line and the program. Reasonable, reasonable. Line is date or sentence. Date is 3 numbers. Sentence is nothing or sentence plus word.
Maybe the program should be also empty, no? Like we have line and program.
It says it's a fatal. Let's look at the fatal error. Start symbol program does not derive any sentence. Sentence. It probably wants us to. It does not derive any sentence. So it says that from program we cannot go anywhere. We can try, but I don't think that's the. Now there are conflicts. Let's simplify. But this is okay. Yeah, this is okay without the program. Let's say program is line. We can do it, right? It's okay as well. Program is line or the program is line and program. No. Now it probably says that that's the ambiguity now because of this. So program is only one line. Can we do like this? Just curious. No. Any ideas? But let's compile this and see that it works. At least this. Flex, and then GCC, and then we run it. It's okay. Oh, sorry, why it's, okay, yeah, 223 doesn't like. It likes this, it likes this, no. Because only one line, right. Hello, it's okay. It understands that this is the whole sentence, including the /n, including the end of line. So now we're still standing in the sentence. So these are the words and words and words and words. And as long as we give the number, it's a syntax error. So this is one long sentence with the /n, one long sentence. And this is the number, the date. And after that, we cannot continue because that's it, because that's the end of the program. That's all the program understands, just one line. How to make it multiple lines, I have no idea. But I would do it like this. I would say that the program is either a line, program is either a line or multiple lines. Oops. No. Okay, you can try it yourself. I don't know. I don't know why it's. I never write code in Bison, so it's just for the sake of experiment to show you that these tools exist. I'll show you another tool right now, which I use. And you know what is interesting is what is interesting to mention is that in the parser there is a mechanism in any parser, a mechanism of recovering from errors. So when you write a Java code, for example, and then you ask the compiler to compile this code, and if you make the syntax error somewhere, or any kind of error, syntax error, so you mistype somewhere, then the compiler does not stop at this line and says, I cannot continue, just this line is the fatal one, and I cannot understand anything which goes after that. It just says line 71 has a problem, and then it continues there, trying to understand the rest of the program, and it does understand it. In most cases, understand what goes after the line 71. Our parser is not doing that way. Our parser just stops and says syntax error and just breaks, and that's it. So we don't recover from error, but we should. So when the proper parsers are done, then recovery from error is an important topic. because otherwise it will be very difficult for your users to, to work with your compiler or programming language if it stops at the first error. So you need to find a way how to recover, and every compiler, every parser generator or compiler of compilers will give you the ability to do that. So it will give control to you. So in this case, when something happens, so this is the function which you can redefine in Bison. I don't know, I redefined it, and I said, and I put just the printing here, the error, but it still stops, as you saw there. So it cancels the program, it stops executing. So we need to investigate how to do it right, and then when the error happens, then it should survive. It should continue from the next token or skip a number of tokens and only then continue. So think about it, how to recover. I cannot show you right now how it should be done in this instrument, but I'll show you in ANTLR. So I'm using ANTLR. So this is ANTLR. It's for Java. Who of you actually are Java developers? 2 people. What else do you use if not Java? What are the favorite languages? The languages you work with. C? Not C++, just C. That's tough. What else? What else? What do you use, guys? Nothing, or just C++, Go, Python, Scala, JavaScript. Anybody on Rust? No, not yet. Okay. Okay, so this is Java. In Java, this tool is quite popular. It's called ANTLR. ANTLR is one of the beautiful things in ANTLR is that they combine together the Lexical and the parser in one file. So you just define the grammar. You don't need to bother with these 2 files like in this Flex and Bison. You just have in one file everything. And in this file, you define the grammar in a quite nice way because it looks very similar to BNF notation. For example, if I want to say that my program is a number of lines, then you just say line plus, and that's it. That means 1 or more lines. If you want to say that there's a 0 or more lines, then you just put a star. So it's much more convenient than many other tools. So it's close to BNF notation. Or you can say that if you want to say, like here, for example, we say that you can group together a number of tokens and say that comment and this can be 1 or more times. Another beautiful thing is that it's clear here from the text. It's obvious which is a terminal, which is a non-terminal. So you see, by the way, these elements, if they are capital letters, then they are terminals. If they are small letters, then are non-terminals. That's the convention, and that's easy to understand. So for example, end of line is capital, so it's my terminal. And in the end of the file, usually people define all the terminals. So here it is. So you say that this terminal means this. So the star terminal, parse it like that. The dots and whatever. So you define it. This is the grammar for a language, for a programming language. So end of line, for example, it's a line break, whatever, something. And so on and so forth. So all the terminals, for example, and also what's very interesting, you can use the regular expressions here. For example, here is how we define the hexadecimal number. So you can write 0x471e, I don't know, 65. So this one will be parsed by this rule. First goes the fixed text, and then goes the rule, it's a regular expression. From 0 to 9, from A to F, from A capital to F capital, and the plus means as many as you want, at least 1. So that's very, very close to the user. It's much more flexible. And then you define non-terminals. You define your own stuff, like program, for example. The program is, and then you say it's the license, which you can skip, which may be omitted. It's the metas block, which can be omitted. Then the objects, which cannot be omitted. And in the end, you put the end of file. And the license, you see license here. The license is a comment, end of line, at least one, and then more and more and more. So you put the comment line, and then end of line, comment, comment, comment. And so on and so forth. What happens with this code, the ANTLR takes this grammar, compiles it into a Java, into two Java classes. One is called Lexer, one is called Parser. And then these Lexer and Parser compiled into the bytecode, and they just work. I can show you how the compile stuff look. So ANTLR, it goes into generated sources, ANTLR, and it generates the tokens here, you see? It gives the numbers to all the tokens. So these are all my tokens with the names, and there are some tokens without names even. So I use them probably like this. So all the tokens, they get their own numbers. They number the tokens. And then for the Lexer, yeah, it gives the same for, I don't know why they have it 2 times. One time file with 61 lines, and the same without one, I don't know. Yeah, and this is the real Lexer. So this is the Lexer which does all the magic. It's pretty long. It should be also, you see, I don't know what it is. Oh, that's interesting. It's not long. It's probably, no guys, I don't know what it is. Serialized ATM. No, I don't know. And this is the parser. That's pretty long. So it does the same, state, the same idea. So internally, it's also states and the same finite automata, which moves from state to state. You see 87 states. So it goes from one state to another, switching if situation is this, if we're in this state, then go to that state. So the same as we would do manually, but it does it automatically. It generates this full 2,000 lines of code, and it parses. So what's interesting here, what I wanted to show you, what is especially interesting, is that sometimes we may artificially, synthetically generate our own tokens, which do not exist in the input stream. That's what's interesting. That's what I just for fun can show you. Imagine this code. Imagine you write the program like we have, which has a so-called, let me find some place where I can show it to you here, which has so-called offside rule. People who code in Python, they know what it is. Offside rule means that, that in the language, your indentation is part of the syntax. So for example, you say print 5 hello, or you can say print 5 hello. So in this case, this indentation means that these 2 lines, they belong to the previous line, and they need to be passed to this function as arguments. Like in Python, you can say if, and then you say print hello. So this implicitly means that this code is equal to this code. So in this case, the indentation just tells us what these brackets tell us in this code. So by indentation, you mean that we need to shift. By shifting right, you just go deeper. What's interesting is that in this case, it's okay. But if you do it like this, for example, if A then print hello, it's one story. But imagine you have this code. So here we put the indentation. Here we put double indentation. And then we jump back, and we need to understand that this print 4 does not belong to the if anymore, but it does belong to the highest level. So the problem, if we parse this text, and we basically, when we parse this text, we replace the indentation during the lexical analysis, when we do tokenization, then we put here basically like this. We turn double spaced into tab, for example. We call it tab. Tab, and then tab. Then the stream of tokens will look like this. If, then A, then tab, then if, then B, then tab, then print, then hello, and then print, and then for. So here something is missing, because we will not be able to okay, let's try to make a rule. Let's try to define the production rule for the parser. Let's say if is if, token if, with some term, the condition, and then the body of the if, for example. No, like this. Tab, and after the tab, we understand it's the body. So that's correct. If A, tab, so far so good. So this is the body for the parser, right? If is this, A is condition, tab is tab, and everything that goes after is the body, right? Because we put the tab here, so it's logical that everything goes after the tab. If we shift everything right, then everything should be moved right. But what about this guy? It doesn't belong to the body. So we need to somehow tell the parser that it stops at some point. So the body should stop at the tab and stop at some other token, at untab, just like we do with the brackets. If we would do brackets, we would call them terminals. We would say if means if, the keyword if, then the condition, then the opening bracket, then the body, then the closing bracket. But we use a different notation. We say we don't need an opening bracket anymore. We need a tab instead. But what about the closing bracket? For the closing bracket, we need something which is called untab. But how do you define this untab? How can you tell at this point, when everything is finished, that it's time to move? We don't even need this. That's enough. Like, we can do this. Print hello. Yeah, like this. Let's do remove BB. Let's do like this. If A, tab, print hello, and then print for. So this is our code. So we need to somehow at this point tell the inject, I mean, we need an extra token because we get rid of this, of the curled bracket. But something is missing, because otherwise it's not going to be possible to understand from this text, from this text, where is the end? Yeah, we say here, imagine print hello. Yeah, so how do you know where to stop? If, condition, tab, print hello, print for, it's gone. This information is lost. The information about that we moved back. So the move back is missing. The move back is lost. The information about that we shifted left is, so that's why we need to, that's how parsers with this, parsers for the languages which use this feature, that's how they are designed. They emit a synthetic token, untab. They put here an extra token, untab. And if you put this token here, then everything is fine right now. Everything is good because the parser can understand. Okay, if is a structure which starts with the tab and ends with the tab. So this is my if, the rule for the if. So in order to emit the tabs, we rewrite the Lexer a little bit. So we created our own Lexer, our own extension of the existing Lexer. So this is the Lexer, which we did. It's not big, but it's interesting. So you see, it extends the default Lexer. So this is the Lexer which is generated, the large one, which is generated by ANTLR. The ANTLR software generates the Lexer for us, but it is not smart enough, and we cannot inject this untapped token in the grammar. So if we just look at the grammar, it's not possible technically to do it here. So there's no possibility. We really need to extend the code which they generate, the Java code. So we extend it by, I can show you what happens, how we emit that token. You see, so every time we move right, we emit, every time we shift left, and we understand it from the, doesn't matter how, so we read the text, we understand from the text what happens, and then if we shift right, then we emit the so-called, the token which we invented, our own token, we call it dedent, and another one we call indent. So indent, when we shift right, we inject the token called indent, and when we emit, when the text goes left, indentation goes left, then we emit so-called dedent. In order to have this indent and dedent, we created those, like I told you, those synthetic tokens, like extra tokens, which are not defined here. We just synthetically tell them that, you know what, there's also two special tokens, tab and untap. So just register them there, but we're never going to tell you how to find them. So if you scroll through the code, you will not see where they are defined. So if all the terminals are defined at the bottom, you see all of them are here, like somehow. But tab and untap, they're not defined. So we inject them programmatically. How do we do this? Emit token. So this command, emit token, it's not ours. So this one is defined by their Lexer. And we just give and say, okay, emit the token tab or emit the token untap. So we programmatically, in the flow of tokens, we inject our own token when necessary. So you can hack the Lexer, and when the Lexer reads the code, you find, okay, in some situation, in some combination, when you see from the text what needs to happen, you just inject the token, and that parsing continues. The parsing understands that, okay, that was the shift right or shift left. That's the idea. And actually, it was not so easy, because if you look at the example again, then in this one it's trivial, because you see that we had the when we see the tab, we just remember that our current indentation is two symbols. So we move right to the two symbols, and then we see the indentation 0. So okay, 0 minus 2. So it means we shift left by 2. But sometimes it happens. Sometimes it could be like this: print hello, and then something else, and then something else, and then something else. So it could be quite deep, and then you shift left, and then here. So in this case, you need to insert untab many times. So that's how it will look in the stream of tokens. Because you do tab, 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 and then at some point you move left by many tabs, and then we inject many untabs. In this case, each this untab will be matched with the right proper tab in the structure on top. That's the most complicated stuff I did with the parsers. That's probably, it was quite interesting and difficult, and everything else was more trivial, and it works. So if you look at our code, for example, of our language, then you will see that it's formatted like this. Let me show some example. I don't know. Yeah, like this. So you see, that's the code. It goes right, but at some point of time, for example, here we shift left. So we shifted right here, you see, 2 times, and then boom, here we shift again left. So usually it goes to the right, but sometimes it can jump to the left. Let me show something else. Yeah, so it goes up and here, for example. You see, it goes up, right, and here we jump left by 1, by 2, by 3. So this position must be clearly identified as a similar to that one. So that's ANTLR. For each, actually ANTLR exists for different languages to my knowledge, but I think for your language where you design, you may need something like that. So some people, it happened in my experience, it happened in my career a number of times. I've seen people who don't know about the existence of these parser parser generators. They just don't know that they exist. They don't know about ANTLR, they don't know about Bison, about this Lex, Flex, whatever. And when they need to do something with the input stream, they just start writing their own parsing mechanism. And usually they don't know about the formal grammar and about these production rules, and they've heard about it, but they don't know how to apply it. And then what happens is that they make the string manipulations extremely complex. So they break the code into parts, into strings, and then there are many ifs, there are many regular expressions, and then the code becomes absolutely unmaintainable and difficult to understand. So just remember that every time in your code, in your program, every time you get some input from the user, from anywhere, and you need this input to be somehow processed, then of course your first choice is just string operations. Split, 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 find the position, start from the position. That's the first choice. The second choice is regular expression. So think about how can you do this, how can you do the parsing using regular expression for this text. If the regular expression becomes too complex, then your next choice is creating the parser, the proper parser. But nothing in the middle. So as soon as something gets more difficult than just a regular expression, then don't make it more complex. Don't continue to stay in the string manipulation domain. Move to proper parser generator. It's not only for programming languages. So here I'm just trying to show you how programming languages are built. But in reality, you're going to build, for example, the string is coming to you from you building a server, and then the client is connecting to the server and sending the request in some format. You don't want to use JSON because it's, I don't know, maybe too complex. You don't want to use XML, it's even more complex. You want some text to come in. In this text, you want the name, the amount, the dollar amount, the time, boom, boom, boom. If this text is separated easily by spaces, then maybe it's okay to split it into parts. But if you make this text a little bit more complicated, then make a parser. Make a parser. These parsers actually, even though they look so complex, they look so large, like 2,000 lines of code for just a simple parsing of a simple text, they are quite fast. So they work fast. This code is well tested. The people develop it for years, so it will work close. The performance will be quite close to just regular expressions, because regular expressions do almost the same thing. And now you probably understand why in most languages regular expression is managed in two steps. First, you compile the regular expression, at least in Java. And then the second step, you use the regular expression. So I don't know whether you know about this, but in Java, in order to use the regular expression, you need to first, well, there are two options. First, you can do pattern. Jesus, I forgot. How to compare, how to match the regular expression in Java. Okay, you do compile, for example, like the expression we did before. I think that's the syntax that's the way it works in Java. So look, we take the pattern, this is the class, we call the static method compile, we give the regular expression to this compiler, and then the compiler created the regular expression for us, and then in this regular, so we can break it into parts to make it more understandable for you. So the compiler first makes a pattern for us, and then in this P we call match. The match happens, and then in this match we ask, did you match? So this is the method which returns true or false. So some people don't understand, why do we need this so complicated step? Why do we need to compile first and then the match first? Now you probably understand, because when you do the compile, it actually gets your regular expression and builds the formal grammar from it. It builds the rules through which this method match will pass. And that's why it's highly recommended to call this line only once. So if you do this in the cycle, if you do it in the loop, then of course you understand it's very ineffective. So if you do it like this, you're going to keep recompiling your regular expression. But it's absolutely not necessary. So that's why people highly recommend, to move it away from the cycle and compile it only once. So this compilation actually is probably the most expensive step. So the compiling is actually understanding the regular expression and building the production rules, building the grammar. And then going through the grammar is fast. So that's what I'm saying. So compiling the parser, compiling the Lexer, it's time-consuming probably operation. But then when it's all ready, when it's all there and it's ready to accept your text, then this acceptance of the text will be done pretty fast. It's going to be just a number of if, and they just go through the rules with the simple forking of the if in different directions. That's your practical outtake from this. So try to experiment with that. It's really fun, creating your own. Actually, there were a number of questions where what kind of projects you can do for this course, and I suggested in the text that you can do your own programming language, you can do compiler, you can do static analyzer, you can do some tool to changing the code. If you need ideas, come to me. I'll give you some ideas which will be helpful for us. I work in Huawei. I work in a company who creates software. So we need some small blocks of code, some small modules, which I can give you as a course project. You can take your own project, of course, whatever you like. But if you need something which will be used in the future, then just come to me. I'll give you a list of subjects, and you will pick what you like, and you will create something which we will use. It will be a compiler, it will be a static analyzer of some sort, it will be maybe a tool to optimize the language, something which you will be able to do in reasonable amount of working hours, and it will be useful for real projects. So see you in 2 weeks. Thank you for today. Bye-bye.